Every hour of every day, a thin cosmic rain of charged particles collides with Earth's atmosphere, some of which eventually reaches the surface. Until recently, observing and measuring cosmic radiation was the domain of physicists in fancy laboratories. But now, thanks to a group of scientists at MIT and the National Center for Nuclear Research in Warsaw, even a dork in the garage like me can be a citizen particle physicist. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're building a muon detector. This video is sponsored by Zod. More on that later. Behold the Cosmic Watch desktop muon detector, or at least the pieces of one. This project was designed as an educational tool for a quote-unquote novice high school student, so I'm a little bit outside my skill level. But who am I to deny you the incongruity of a civil engineer soldering tiny components to a circuit board while talking about cosmic radiation? Before we get into the engineering behind the device, first we need to know a little bit about cosmic rays, or at least our current understanding of them, because there's still a lot of mystery behind their origin. Spread throughout our galaxy, and indeed the entire universe, are stars. And on occasion these stars explode, creating supernovae. And when they do, they eject a tremendous amount of interstellar material, also known as star stuff. This material is traveling so quickly that it generates a shockwave of superheated plasma. These shockwaves are believed to be the origin of most of the universe's cosmic rays. The superheated plasma accelerates the particles to unimaginable speeds, and some eventually reach the Earth. When they slam into Earth's atmosphere, they produce a slew of secondary particles with crazy names like pions and kaons that eventually decay into muons, the particles that can survive the trip through the atmosphere and even penetrate into Earth's crust. Scientists observe and measure muons and other cosmic radiation to learn more about the universe with fantastically complex and expensive equipment. But this detector opens that door to any student or citizen with a soldering iron and a good magnifying glass. As fun as it is to dive into particle physics, the coolest part of the Cosmic Watch project is the engineering. The device uses interesting components and clever circuitry to make it possible to detect and count these cosmic rays. And it all starts with the scintillator, a piece of plastic with a very special ability to absorb the energy of a radiation particle and re-emit that energy as light. As a muon passes through the scintillator, a burst of light is created. It's not enough to see with the naked eye, but it can be detected by the attached photomultiplier, which is essentially a supersensitive solar panel capable of measuring even just a single photon. The photomultiplier converts the burst of light from the scintillator into an electric signal. But this signal is extremely short, less than a microsecond, which is hard to detect. The Cosmic Watch uses an Arduino to measure the signal, but it can only take a measurement about once every 6 microseconds. You can see how easily it would be for the Arduino to miss the muon pulse. So the Cosmic Watch uses a peak detector circuit to amplify and stretch out the signal so that it can be detected by the Arduino. This shot from the oscilloscope shows the output from the peak detector in yellow. If I zoom in on the timescale, you can see how short the actual pulse from the photomultiplier was. Once the Arduino detects a pulse, it sends a signal to this LED to let you know. The Arduino can count the amplitude and number of pulses to measure the average detection rate. It can record each pulse on a memory card, and it can even send the data over USB to your computer. I built 2 detectors, which makes it possible to measure the direction of a particle and helps eliminate false triggers from other types of radiation. When operated in coincidence, a muon is only recorded if it was detected by both devices at the same time. In this shot, the bottom detector is the slave, which only blinks if it detects a muon at the same time as the master above. Now that the detectors are assembled and working, it's time to do some science, and there's a lot of science you can do here. This is such a great educational tool because the measurements are so simple. Most of the experiments you can do are really asking the same question. Does this particular parameter affect the rate or intensity of cosmic rays detected? Spencer published some very cool experiments he used to test out the detector, including how the rate changes at ground level versus down in a mine, and how much the detection rate increases during a flight on an airline. But you guys know how much I like to make cool graphs, so I also designed a few of my own experiments to test out. First, I know that muon formation happens in the atmosphere, and I also know that some atmospheric properties like temperature and stability change throughout the course of the day. So I hypothesized that there might be a measurable difference in the muon detection between day and night. To test this out, I left the detectors running in the same spot for 24 hours. I started the count at 6:30 a.m. when I left for work and reset it at 8 p.m. to leave it overnight. The rates and measured intensities were almost identical, suggesting that if there is a difference in detection rate, it's only a small effect. The null hypothesis prevails. Next, I wanted to test how the direction affected the detection rate. You can leave these detectors blinking on your desk, but it's still hard to imagine the cosmic rays passing through your personal space if you don't know what direction they're coming from. My guess was that most would come from directly overhead because it's the most direct path through the atmosphere. I set up the detectors one on top of each other for a day and then side by side for a second day. My results agreed with Spencer's that the detection rate from side to side was about half that from straight up, and you can see that the measurements from the horizon had more low energy detections than from straight overhead. My last experiment obviously needed to be related to concrete, because I said I was going to keep making videos about concrete and then made a muon detector instead. My hypothesis was that layers of concrete would provide some shielding and attenuate the detection rate. So I left the detectors in coincidence mode, running in my car, and parked on a different level of the parking garage at work for 3 days. Measuring only the particles coming from straight up, there was a small but obvious reduction in the detection rate for each layer of concrete in the parking garage above my car. I love this project because it takes something that is not only invisible, but also maybe unknown to most people, and makes it tangible and approachable. If you're an educator, this is an awesome tool for exploring the scientific method because the experimental design is fairly simple, the data collection is easy, and the subject matter is fascinating. Huge thanks to Spencer and the other folks associated with Cosmic Watch who developed this awesome device and helped me with the video. Check out the link to their website in the description. Thank you for watching, and let me know what you think. Getting started in electronics can be intimidating at first. If you're using microcontroller boards in your projects like the Arduino and the muon detector, you not only have to learn about circuits, but also about writing code. With Zod, you don't need to be a programmer to use a microcontroller. With its visual programming language and well-written tutorials, you can get started on awesome projects with almost no learning curve. Building programs visually with nodes makes controlling your electronics projects fun. Zod is open source, and best of all, it's completely free. To get started, go to xod.io or just click the link in the description below. Thank you for watching, and let me know what you think.